Hey Geometry Geniuses, for this video on 10.2, we're going to be taking a look at the area of a trapezoid. Looks like this. We'll also take a look at the area of a rhombus, parallelogram that we saw a few sections ago. And we'll conclude with the area of a kite. You've flown one of those before on a nice blue day. You had that little string. It was flying in the air. Maybe you didn't notice it, but these have diagonals on a kite, the blue lines that I'm showing in here, which will soon be important as we take a look at those areas. Rhombus is also going to have those diagonals too. So we've seen the vocab before, and I just want to throw it back into the mix. The agenda for this video is taking a look at real-world examples, just for the trapezoid, really. We'll continue with a warm-up, and we'll conclude with some examples for taking the area of a trapezoid, rhombus, and kite. Let's get to it. Real-world example. Two trapezoids that I found around my house would be this cowbell that I got from a charity bike ride I did, going from Philadelphia to Atlantic City. Makes it sound like this. And also this coffee cup here, another trapezoid that I had around the house. And so finding the area of these, we'll soon see, isn't too difficult. So let's get to it. With this first warm-up, before we dive into the actual area of a trapezoid, see if you can find the area of this parallelogram seen here. If you need a refresher, recall that the area for a parallelogram is base times height. In this case, recall that since this is 60 degrees here, we can assume that this height is going to be creating a right triangle. And this would have to be 30 degrees. This would be 90 degrees. Since this is the hypotenuse for a 30, 60, 90, we can assume that this is two versions of the smallest side. So we're able to say that the smallest side in this case is going to be 3 units. And what does that make the height? What do you think? That would make the height 3 root 3. And if we're going for the area in this case, our base up at the top and the bottom is 10. So we would take 10, multiply that with our height of 3 root 3, and get a total of 30 root 3 units squared. Pretty simple warm-up. As we move towards the area of a trapezoid, this gets a little bit more complex, taking the area, where we see that this is now half the product of the height and the sum of the bases. Take a moment, pause the video, get familiar with this. So recall, a trapezoid will have 2 bases, one on the bottom, one up top. The height, which is sometimes referred to as the altitude, which we saw, I believe, in 10.1, the previous section. Little quick explanation as to why this works. If we break the trapezoid into 2 triangles, where we have this triangle here, where our base is B2 and our height is H, the height of this height of this larger triangle would be 1/2 B2 times H. And if we look at the other smaller triangle, we can take the area of this where our base is B1 and our height is still H. So the area of that would be 1/2 base 1 times H. And if we add the two together, we see that these definitely have 1/2 common with both of them. And they also share H common with both of them. So really, it's just adding the 2 bases, multiplying it with the height, multiplying it by 1/2. Pretty simple. Let's take a look at this first example here. Nevada, great state. Roughly shaped like a trapezoid, and we're being asked to find the approximate area of Nevada. Simple task. Although at first glance this doesn't look like a normal trapezoid that we saw way up here, don't let that confuse you. Try to draw it again. Where hopefully you can see that the height of this is 309. This top base, the smaller of the two, you can call 205. This you can call 511. Recall that for our area, we're taking 1/2, multiplying it with our height, which in this case is 309, and multiplying it with the sum of which two numbers? What do you think? Hopefully you're saying 511 and the 205. If we use a calculator to take this further, we're going to take 1/2 times 309 and multiply that with 716. Let's let the calculator do the rest. So let's just do 0.5 times 309. It's like 309. Multiply that with, what was it again? 716. Yep. 716 gets us 110,622. Let's take that back for the area. So 110,622. This was miles being squared. Because remember, we're going for the area of this. Pretty simple, right? Just have to draw a little bit more than normal. If we have this trapezoid where our base lengths are going to be 10 and 15, when you're really good at these problems, you can just kind of draw them out as you're reading through them. And there's a height of 6. So let's assume that it looks something like that. All right, what's the area? Pretty simple for this. We have 1/2, multiply it with our height of 6, multiply it with the sum of 10 and 15. So we're taking 1/2 times 6 times 25. So this would get us 3 versions of 25, because half of 6 is 3. And this would get us 75 centimeters squared. Simple for that. Another 30, 60, 90 coming up. You got this. We can note that from P to Q, this is 7. We know that from S to R, this is 5. What are we missing? We're missing our height. But don't worry. We know that from S to R, this is 5. So what do you think the distance is going to be from here to here? Hopefully you're saying 2. So lo and behold, we have another 30, 60, 90. Told you those were not going to go away. So that would make our height here 2√3. So then now we know our height. Boom, 2√3. We have a radical to work with here, but don't let that throw you off. We're still taking 1/2 times our height, 2√3. Taking the sum of our bases, which is 7 and 5. So we can rewrite 1/2 times the 2 is just one version of √3. Multiplying that with 12. Getting us, boom, 12√3 meters squared. And it's okay to leave the radical in your answer. As long as you did it right, leave it. Why not? Let's move along to the rhombus, which we've seen before. We can break this apart and think of this as if we have 4 triangles in the rhombus. And you can think of this further using the diagonals, that these kind of make up the side lengths. So you can think of this as if you have this top portion where the base is D2, and the height in this case is half of D1. And then if you're taking the area of this triangle, this would be half of your base, which is D2, times 1/2 D1. So really for the top portion, at least, it would be 1/4 D1 times D2. But remember, you have that other part. So that's why we end up saying that collectively the area is 1/2 D1 times D2, where D1's the diagonal and D2 is the other diagonal. So that's something to think about, that the top portion's a quarter D1 times D2 up here, and then the other portion's the other half, or the other quarter, D1 times D2. Because, you know, if you take half D1, D2, you add that, D1, D2, 1/2 D1, D2. A little bit of theory on that. We're actually able to say the same thing about the area of a kite, which is awesome. Makes our life a lot easier. Also uses 1/2 D1 times D2. All right, great. Let's keep it moving. A few more examples here. We're almost done. We've got the area of a kite first. We know that our diagonal stretches from K to M, hitting this 5 and this 2. So we'll call that D1. The sum of 2 and 5 is going to be 7 meters. For D2, the sum of 3 and 3, it's going to be 6. Recall that we're taking 1/2 D1 times D2. So we're taking 1/2 of 42. It's going to be 21 meters squared, right? Don't forget that it's squared. Simple, easy stuff. I really like this problem because we have to take apart the rhombus and we have to use 30, 60, 90 triangles. I'm always into that. So I know that with this distance from here to here, this is 4. And I know that this is 60 degrees. So that would make this 4 the smallest side. So what do we know about this length from here to here? Maybe I'll break this apart over here further. So if this was 4, this is 60, this is 30. What's this going to be? Hopefully you're saying 4√3. And again, we have another version of that triangle down this way. So collectively, this is 4√3, this is 4√3, this other side from here to here is 4. So in blue, this diagonal here is going to be 8. In red, this diagonal here is going to be 4√3 times, 4√3 plus 4√3, so 8√3. 1/2 times 8 is going to be 4. 4 times 8√3 is going to be 32√3. And we have meters squared for that area. I don't think this section's too tricky. We kind of luck out in a sense that the kite and the rhombus have the same formula with 1/2 diagonal 1 times diagonal 2. Recall that again. I don't think the rhombus portion's too bad either. Just 1/2 the height times base 1 plus base 2. Use parentheses for this also, just kind of seclude that.